that is my Ender3 Pro, and I'm very satisfied with that printer. Now, I've heavily modified it, doing things such as putting this flexible magnetic build surface on there. I've got a Duet board, that's the Duet Maestro controlling the thing, and I connect it via Cat5 Ethernet cable to the router, so I'm able to send prints wirelessly just from my computer. Even though this thing lives in the garage, it really is kind of my go-to printer, and I print most of my stuff on this little printer that I kind of didn't think I was going to love it as much as I do when I was building it. But all that being said, and as fantastically functional as it is, it does have one major problem still left to solve for me, and that is the fact that it doesn't print well with PETG. Like, I don't think any printers really do, unless you have the ability to wipe the nozzle. Now, I was inspired by the new E3D tool changer to put a nozzle wiping apparatus onto this printer. So that's the subject of this video, and hopefully when we're all done, this will be a printer as good as anything out there. I mean, even the Prusa doesn't have a nozzle wiping thing, I don't think. So yeah, let's give it a go. Okay, for those of you who are too impatient to watch a video from start to finish in its entirety, here's your too long didn't watch synopsis. Basically, I put this wire bristled brush here just off the side of the bed, attached to the x-axis, so it's always in position no matter how high up the nozzle is up off the bed. So you've seen previous versions on Thingiverse where there's a wire bristle brush sitting up here in the front, but that only works for the very first layer. So this will work for all subsequent layers, and it allows you to keep your nozzle clean when printing PETG, which can be kind of problematic. PETG has a tendency to sort of like work its way up the nozzle for some reason. You just have a lot of buildup with PETG when you're printing. So this should keep the nozzle clean, and you'll avoid jams and all of that. So it's a pretty great little upgrade. Now, the reason I made this video kind of longer than this synopsis is because I got a lot of comments in previous videos, people wanting to know my process, like how I do one of these projects from start to finish. So including, you know, drawing in CAD and all of that. So this is literally just a kind of a journal, how I made this, I guess you could see it. So stay tuned, maybe you'll learn something, and yeah. So this is the plan. The print head here can move all the way to there, and at that point, this bolt, which is holding the pulley right here, is actually colliding with the diagonal of the bracket here for the vertical motion. And so I just need to cut that bolt a little bit short, and I think I need to grind down the nut a little bit as well. But after I do that, I should be able to get quite a bit more travel. The next thing it's going to hit is right here. This bolt head is going to collide with that. So I could put a lower profile bolt head there to also, you know, get me even more travel. But even as it stands right now, without cutting any of those bolts short, the nozzle still comes quite a substantial distance off the edge of the bed. So this is a Harbor Freight, you know, cheapo China brass or copper bristled, what is it? Just a wire brush, and that's going to sit right there, just like that. So I'm going to cut the head off of this and figure out a way to mount it right there. So that's what we need to do, basically. Just cut these bolts and then make a bracket that comes off of here to hold that. Now, unfortunately, there's nowhere to mount the bracket to easily. I was thinking of using these two screws and maybe making a new portion of this all out of 3D printed plastic, but this is a rather important moment. It has to stay stiff because it keeps the belt tension. So I don't want to replace that with plastic. You know, that's metal at the moment. So yeah, I'm going to drill and tap into the bracket here instead on this lower side. And because the bristles have to sit pretty much right there, the screen is in the way. So the first thing we need to do is move the screen farther forward so that the bristles on the brush can sit back behind it. So let's jump on the computer and design up that geometry right now. To mount the extension block, we're going to use these two extra bolts in combination with the two bolts that come stock with the screen. So here in Rhino, let's just draw it. We're going to start out with a primitive object. That's a cube here, and it's going to be 40 millimeters cubed because that's 40-40 extrusion rail that the printer is made out of. And then what we're going to do is draw a point object here, and we're going to move that, 10 millimeters down and 10 millimeters up, just like so. And then we'll just do a polar array. Now I need to find the center of that box for this polar array. So I drew a line, and that way I can snap to the center and do 4 objects. And just like so, we've got a polar array. Okay, so the hardware that I'm going to be adding has a shank diameter of 5.5. Well, that's how big I need the hole to be, because I need to clear it. I need to have enough clearance from the 5 millimeter bolt. So I want a little bit of wiggle room. And so then I'll just copy that across the diagonal. Then we'll do what's called a Boolean difference there. So we'll just subtract these basically holes using those 2 cylinders that I just drew. Now the bolt head on those 5 millimeter bolts happens to be 10.5 millimeters. Now the bolt head's a lot smaller, but the washers that I'm going to use are 10.5 millimeters. So, and we'll just go all the way to the base there, and then we will copy it. Actually, we'll move it 17 millimeters up. And the reason we're doing that is because I have 17 millimeters of shank on that bolt exposed here in the spacer block. So once again, we'll just copy. It sees that there's a point inside of there, and it sees it. See, it grabs that point, even though it's kind of invisible to us. So I'm just grabbing it from that point and putting it over there. And then once again, Boolean difference. Boom, boom, gone. Delete these, done. And then let's take and grab the dealio again. And this is going to be a 4.7 millimeter shank length. And the reason for that is because that's the right sized hole for the stock hardware to just thread straight into the print. I won't have to do any post-processing. It just threads right in. The layer lines kind of act like threads, and everything just really works. So the length on the stock hardware is about 8.5 millimeters. So actually we want to go negative 8.5, and there we go. Copy that one there. And then once again, Boolean difference. Now there's a way to, when you Boolean difference, to have it delete the object that you just subtracted with, but I like to keep it just because I don't always want to get rid of that geometry. So I do that part manually. All right, so we've gotten rid of those point objects. We no longer need those for reference. And the only thing left to do is to sort of round over these corners. That's generally called a fillet, but there's a slightly geometrically different way to do it with what's called a blend edge here. So we'll just blend edges, and the radius is 2. So we will just select there, 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 and there. Press enter and enter again. There we go. So there is the geometry that I want to print. So I will turn this into a mesh, and then this mesh here I can export as an STL. Now here in Simplify 3D we can see that STL after I've imported it here. And what I've got set up is a multiple layer print. So basically here in Tools, variable settings wizard, I've got 2 heights set up. And what that's accomplishing, if I prepare to print, you can see that basically I have support material, which is what I need for this very top layer. Bridging is not the best, and I only want to print three layers of ceiling there. So having some support material there is kind of it's a good, nice thing to have. And that's only 15% support material in a rectilinear. So every other layer, it's going diagonally in the different direction. So that should be perfect for helping the ceiling print. But down here, you can see it's also the support material starting right there. But it also supports the bottom of the holes for the for the stock hardware to mount into. So basically I start support material a little bit below those holes, and the support material here is just bridging into space. So I got to turn my part cooling on, and then you can just see in this way I save a bunch of time printing, and so my print's only going to take 1 hour and 23 minutes. So a very fast little print. It's just got 2 walls of thickness, kind of almost 3 once you include the support material extra bits. But yeah, this should be plenty strong for our purposes, and it's a quick print, so you can see why I did that. Okay, let's get this printed. I was a little impatient to peel it off the hot bed, so the base got a little bit warped, but that won't matter at all. We're going to install it right there behind the screen, so let's make that happen. By the way, this is printed with PLA material, but I'm not going to be sticking this printer inside of an enclosure or anything like that, so really shouldn't make any difference. The only thing to worry about would be the creep. You know, but this isn't really a structural member. It just sort of holds the screen in place, so I'm not worried about things moving around too much on me. Okay, that'll do nicely. Screen is secure, and we can now fit this brush back behind there and hold it in place to where the nozzle can do that and clean itself up. And hey, contrary to popular belief here on the internet, you can do that all you want to these boards and it's not going to fry the board, especially if you're running a duet board like I am. But even the stock control boards these days are robust enough to be able to handle that. Back in the day when 3D printing was brand new, there was a chance that that feedback could fry your electronics. But today, it really doesn't matter. Let's get this brush head mounted. So here you can see I am measuring the actual brush head itself and putting it into Rhino, drawing it up. And then the next step was to kind of figure out where it's going to sit in space relative to the frame of the printer. And so I took a lot of measurements, and it's kind of a trial and error thing. You know, some of your measurements aren't quite right, and you just kind of double check yourself, taking measurements off of different places. And anyway, here I am drawing the metal bracket, the portion of the printer that we're going to screw into. And then I needed to figure out exactly where the nozzle was going to fall. So I drew the nozzle floating in space all by itself. There's really no need to draw the rest of the hot end. We just need to know where the nozzle sits. So reposition the brush head so that it brushes the nozzle, and then, you know, double check my work. So then it's time to model the screws. So here's the set screw that's going to keep the brush head, you know, from falling out. And then the next thing to do is these flathead screws. Now I used flathead screws because I want a really low profile. I don't want any collisions happening. So I don't want my screws protruding past the bracket. Okay, so this is the portion of the bracket that's going to wrap around the brush head. You can see the screw at the bottom. That's the set screw that's going to hold the brush head in place. And then there's the profile of the bracket extruded out. There's the whole bracket. It needed a little thickness, and then I just chamfered the edges, the corners there, so it just kind of makes it pretty. Now the next thing to do is just sort of color everything, all the individual components, just to give myself a better idea of what I'm looking at. It just helps me critique my work. And then finally I had to make the slots so that there's some adjustability in the bracket. And I didn't quite know at first how big to make the slots, but eventually I figured it out. And this is, I'm just taking those screws and kind of turning them into the slot shapes so that I can subtract with those slot shapes. Now the geometry here was a little bit messed up, so I just had to kind of fix it a little bit before I could actually use it for that Boolean difference operation. So there we are, final bracket. While I'm waiting for the bracket to print for under here, I'm going to disassemble the hot end. I need to access this bolt head, which is currently kind of hidden behind the fitting for the Bowden tube. And I also want to grind away some of the metal here on this hot end bracket so that we have a little bit more clearance around that bolt head right there. I am pretty proud of this compact BL Touch split cooling fan duct, but in order to get to the hot end, you do have to disassemble the whole thing. That's disassembled, and I've turned this bolt around backwards. The low profile head here, just like this one, is clearing the bracket nicely, but I do still need to cut off that extra length of bolt just so that I can clear the hot end. Now you can see the bolt colliding with the bracket there more clearly, so I am going to grind into that just with a hand file, no big deal. Now, before I printed this up, I actually figured out the problem that I was going to have where the pulley wheel was going to be colliding with the geometry. So I did this whole recess cut out of the side there in order to give myself some clearance. But you can probably see the problem that I'm having. This tang that bends underneath, that captures the belt here, and it is colliding with the part. So I've shortened up that geometry a bit. You can see it right here. This was the second iteration, well, the third iteration really, but design, prototype, test, rinse, lather, repeat until you get a workable part. So that will sit in there nicely just like so, and we should be able to clear everything. And just this will be the collision point, the stopping point. So now what I need to do is use my drill with this, what is it, a 2.72 millimeter bit. I don't have metric bits, so that's a, SAE bit, and basically it'll still work for tapping. Here's my tap. So once I've drilled that hole out, I can tap those threads into the aluminum. But this is a little bracket, or I'm sorry, a little guide that I've made just to put right under there like so, and it puts those holes dead center in the middle of the slot. So you can see that these bolts are slotted. So when I drill those holes using this this template, they should be perfectly in the right spot, and everything should work out well. So basically just drill the holes, tap them, cut that bolt head off, and reassemble the thing, and I'm done. And that's how it's done. So by the way, this is the handle, so you can go get the same brush at Harbor Freight. Now, you can see I've got the brush head, so it just barely clears the bed. So as soon as the nozzle leaves the edge of the bed, it will start wiping. And everything's adjusted pretty well. My screws here are a little bit crooked, and that's just because my my little jig here moved as I was drilling. So if I was going to do this again, I would drill the middle hole and tap it, and then sink a bolt into it and tightly hold it down in place before I drilled the second hole. But hey, it works just fine, so that's all that matters in the end. Now I do have one sort of problem, and that is the fact that the bristles on the brush are touching the part cooling fan. So, or the fan shroud, I should say. So this will wear out eventually. Now that is made out of polycarbonate, so it's pretty tough, but I'm going to have to redesign that, clearly, at some point. Now it'll work just fine for now, but it's not good enough for the long term for me. So anyway, all that's left to do now is to figure out the new travel limit of the bed, and to put a, basically a G-code wipe command at every layer shift. So every time we do a new layer, it's going to come over here and just wipe on the bristles and go back to printing. So just a quick wipe move, which should keep that nozzle nice and clean during a print, and I shouldn't have any more, skipping or jamming issues on my PETG prints. So let's get all that set up and give it a test run. Here's a better view of that cutout that I made with the hand file, and you can see it nicely clears the bolt head. The printer is all back together and hooked up to the router with a Cat5 Ethernet cable there in the garage. And here I am looking at the printer through the web interface through my web browser. So we can modify everything we need to modify about this printer through the web interface. I really love Duet control boards. Anyway, if we click on settings here and then config.g, and then we scroll down here to the axis limits, we can see that my axis for the X direction is set to 267.5 millimeters. Now, that's the distance that I measured for my machine. That's the distance it can travel off the bed. And that's just dependent on how much I ground away on that bracket on the X carriage. So depending on how far you grind into the X carriage, your number here might be smaller or larger. So if you are running Marlin instead of Duet, there is a way, of course, to change this travel limit in Marlin as well. You'll have to go in through your Arduino IDE. It's not nearly as user-friendly as this, but yeah, it'll work. So yeah, change that and save changes, and you'll be done. And the next thing to do is to open up your slicer. Okay, so my slicer here is Simplify 3D. You could do pretty much the same thing that I'm about to do in any slicer, Kira or Slick 3R, or whatever it is that you're using. But basically what you want to do is modify these scripts. So you'll have a starting script and an ending script, and for most people, those are the only two that they will ever touch. But we're going to get into the layer change script here. And every time that there's a layer change, this is the series of G-code commands that we're going to implement. Now, I've written all of these by hand, so let's just go through them real quickly. The first line is G60 space est1, and what that does is it basically memorizes the current location of the print. So it just stores into memory the current location. Then we're going to change to a G91, which sets the machine into being relative coordinates. We're going to change the feed rate to be pretty slow, so that's about 30 millimeters per second, so pretty slow. And that's just so that we can do this retraction movement. You don't want to do retractions too quickly with PETG. So then we're going to change it back to absolute coordinates on the machine, that's G90. We're going to change the feed rate up to 5,000 for rapid movements. We don't need to wipe slowly. We want to wipe quickly. We don't want to take too much time doing this. And then we'll have a G0, that's a movement command, move the x-axis to 267.5, which we already established is the far limits of the bed there, of the brush. So the next thing we do is a G61S1, and what that does is it calls back into memory the position that we saved at the very beginning, and it moves the printer to that position. Change back into relative coordinates with a G91, change the feed rate to be slow again, G0 F2000, then G0 E4, which is basically repriming the nozzle to make up for this retraction move that we did up there in the beginning. And then we're going to change the machine back into absolute coordinates so that we can continue with the print. And this is the result. So you can see all of these red lines are the manifestation of that layer change script that we just wrote. And so if I click through the actual movements, the G-code lines here, we can see that. See right there, that's the nozzle printing. So we're going to finish printing here, and then you can see it just sends it right there. Just sends it to the edge of the bed, does the wipe. It has to run through a couple more G-code commands that don't have anything to do with movement, and then it sends it back to the place where it just left from, and it resumes printing from there. So really cool. This should work out quite well. Let's see how it performs in real life. Okay, so this first layer is just about to finish printing, and once it's done, it's going to head on over to that brush and wipe itself off. Pretty cool. It'll do that at every single layer. There you go. What might be the most useful upgrade to add to your printer since the advent of part cooling and automatic mesh bed leveling, or bed trimming, whatever you want to call it. Just super helpful when it comes to PETG printing, and I am really happy to have that functionality now here on my Ender3, which is my go-to printer these days, like I said in the intro. So if you want to get your hands on the geometry, like the printable geometry, go ahead and head on over to my Patreon page. So I give any and all of the digital files that I make for these videos to my Patreon supporters. It's not like you can only get one file from me. Just, go become a supporter and it's all yours for the taking. So yeah, but to the people who are already Patreon supporters, thank you. Thank you guys, as usual. So much gratitude. Without you guys, I would not be doing this. I would have quit a long time ago, and you're the real heroes. So that's it for this video. Thanks for watching. See you next time.